Hi everyone, welcome back. Let's get started. So, lecture 3. Today is sort of the last lecture where we will talk about more theoretical topics on lossless compression, and then next lecture onwards it's mostly being be algorithms. So today we will cover 3 topics. The first one is something called Kraft's inequality, which you will see soon. I will explain when we come to it. The second 2 are really sort of the main result of lossless compression, which tells you what is the best possible lossless compression you can do. And so that will be sort of the takeaway. And that's what we will then try to achieve for the next several lectures. Okay, stop me anytime with any questions. So let me talk about SCL. So what is SCL? SCL is Stanford compression library. I will show you how it looks. Yep, please.
For partners, can we just post an ad to ask if anybody is looking for partner?
Projects? Oh, for homework. Oh, yeah, like a study group sort of thing. Yeah, sure. Yeah. But you have to submit the homeworks individually.
Oh, okay.
Yeah. For the projects, you can do it in groups.
Yeah.
Any other questions?
You can also use it to ask any questions, especially if you are stuck in coding for maybe more than 5 minutes, don't know what exact functions to use. Shubham will talk about it.
Yeah. So as I go through the SCL thing, basically like the aim of this library is to make your life easy, to make it easy to learn things. But sometimes if you are not as familiar with Python or if you're not familiar with like this style of Python or something, it might become an obstacle. We don't want that. So if you get stuck at any point in anything, just reach out ASAP so that we can help. We have tried very hard, learned from last year. So hopefully this year will be a much smoother experience. Okay, so SCL, what is SCL? SCL, Stanford Compression Library. So this started last year, mostly Kedar's initiative. So what you see, like if you want to learn about compression, right? You learn about the theory, you learn about the basic algorithms, but then you go to find some actual implementations. You want to use it in your research, and you suddenly run across like for some of the implementations you find, for some of the algorithms you find Python implementations that are possible to read, but most of the times you just see a C file with like very low level C, sometimes even SIMD and like that sort of very low level code. That's very hard to read for a beginner. So you don't understand anything. And so it like you can't understand the algorithms, so how will you use it in the research, right? So the point here was like we want like many basic algorithms are hard to find, and right, efficient implementations are hard for beginners to understand. And just understanding the algorithms like we understand in class, right, that's not enough to actually implement it. So unless you like actually implement it, you will find that there are many gaps in your understanding. So with that aim, we like started writing some common data compression algorithms research implementations, right? Aim is not to be like the most efficient implementation, but something that you can read and understand. Plus the other aim was to have like a framework so that somebody could like modify these, make their own compressors on top of this, that sort of thing. And the last aim was more selfish, like we ourselves wanted to actually implement these, at least if we want to call ourselves data compression researchers, better that we understand some of these in more detail. So with that in mind, let me give you a very quick tour. So this is the course website, which I hope you have seen. You see fall 23 here, right? Don't go to the fall 22 website, right? Use the fall 23 website, bookmark it, so that because on Google sometimes it might lead you to the old website, right? The homework will be on the assignment tab here, homework 1. If you go to logistics and then you go to useful links, the top useful link is Stanford Compression Library. So let's go there. So it's on GitHub. Right. I guess I will just briefly walk through what's in it, right? So basically it implements a bunch of different common algorithms, a lot of which you will study in class, right? And it will be very useful like for your projects, for example. many of the students last year did projects on extending a bunch of these, right? And then you can contribute back to the library. So there are some prefix-free algorithms. There are some other entropy coders, more efficient ones. And there are some external libraries imported here. There is a getting started if you want to install it and so on. This will all be part of the homework, so you will get to do this as part of the homework. Let me just, so that you get a sense of what's in here. So if you go to the SCL, I hope you can see it. Yeah, okay. Right, so there is a utils one, which I will go through very quickly first. So the first thing you will encounter when you start implementing a data compressor is that machines work with bytes, but oftentimes many of these compression algorithms work with bits. So you need various types of utilities to convert from your bit arrays into actual bytes that you will write to the file and so on. And you will run into this in the homework. So this bit array util file has bit width and integer to bit array to integer, random bit array, just a bunch of useful functions. So in the homework, what you will find is we have tried to provide you hints on what functions you should try to use, right? So just look at the homework code, the starter code, and hopefully it helps you. There are a lot of algorithms we saw last time, right? They work with trees, so there are some tree related utils, some miscellaneous stuff, testing. Right, then many algorithms, as you've already seen, work with probability distributions, right? So you want to sort a probability distribution. Last time we read about Shannon codes where you needed some sort of sorting. You want to normalize things, you want to do cumulative distributions. So just this sort of thing, right? Lot of utility stuff. Enough utility. Let me talk about one thing very concrete thing we saw in class. I think it's in compressors. Yeah, so if you remember last time we talked about prefix-free codes, and we saw that to decode them, you go through a process where you keep on adding a symbol and then you try to decode it. So this is sort of the structure of many of the functions here. So it's a prefix-free decoder, which needs to have a decode block function and an encode block. Oh no, this is just a decoder, so it will have a decode block function. And to decode a block in a loop, the loop you just see on the screen, let me zoom in. While number of bits consumed is less than, basically as long as you have bits left, you try to decode a symbol. And then in a loop, basically you decode one symbol at a time. That's prefix-free decoding. And you might ask, how do I decode a symbol? Let's see. Yeah, so here is decoding a symbol. So line 166, you set num bits consumed to 0. Line 170, you set current node to root node. So this might be bringing some memories back from last lecture where we saw that you start from the root of the tree and then you keep going down until you hit a leaf and you decode that leaf and so on, right? So all of this is implemented and you will use it in your homework, and you can read it if you don't understand something in the lecture, because often for many of us, reading a code helps us bring more clarity than just a sort of a vaguely drawn diagram in the lecture. So there will be a tutorial on SCL which will help you get started, which will be posted later this week sometime. So that should be very useful for you as you start your homework. And again, if you're struggling with anything that seems to you that it's our fault or it's SCL's fault, talk to us. We will help you out. Any questions on this? Yeah, I'm sure you will have questions once you get started. But for now, let's move on. Okay. So last time's quiz, we will come back in a bit. Please be patient. I want to cover one topic which will be useful to talk about the quiz. Okay, so last time we talked about prefix codes. So prefix codes are codes where no code word is a prefix of another code word, and we saw that it really simplifies the decoding. And one way of decoding was this tree-based thing where you start from the root, you go down the tree and so on. Right, I've drawn one of those here where if you see a 1, 0, you go this way, then you go this way. and you decode a B, and then you go back to the root, and then you see like a 1, 1, 1. So you go to D, you decode D, you go back to the root. I won't spend too much time. I think you might have gotten some practice in the homework, in the quiz. Then we defined a good code. I just gave you a thumb rule, asked you to believe. We will show this time why this held, but we said that a good code has the length of a symbol, the length of the encoding of a symbol is roughly the log of 1 over px. And then we actually constructed a code called the Shannon code, where the lengths were actually very close to the promised good code. For Shannon code, we did the construction. Construction was very simple. We sorted the symbols according to their length, and then we just basically pick a code word that doesn't violate the prefix precondition. And I think you had some homework questions on that. Then we did the proof for why that construction works. Even if you didn't fully follow the proof, that's totally fine. We won't be using that. You will see a proof which is very similar, so hopefully that helps better understanding. Okay, so first topic today is Kraft's inequality. What is Kraft's inequality? So last time we saw that a prefix code is equivalent to having your code words be leaves on a binary tree, right? But so when we say prefix code, we mean no code word is a prefix of another, leaves of a binary tree. These are very sort of English sort of representations of the thing, not as mathematical as some of you might like. Today we will see a characterization of prefix codes which is very mathematical. You can see a prefix code is equivalent to satisfying a certain inequality, which we'll just see in the next slide. And this will be very useful for the rest of the lecture and beyond. So this is the inequality. So first part is the forward part, and then we have a converse. So given a prefix code with certain code word lengths. Oh, by the way, these will be posted on the website. So yeah, if you want to take notes, but if you don't, then that's fine. Okay. So for any prefix code in the world that has certain code word lengths L1 to Lk, the sum of this quantity, summation I equal to 1 to k, 2 to the minus Li is less than equal to 1. Right? And we'll see this come up again and again. So for now, okay, this is something. And maybe the converse part might interest some people more, which is that given any set of integers L1 to Lk, satisfying this inequality, there exists a prefix code with lengths L1 to Lk, right? So basically having a prefix code is equivalent to satisfying Kraft's inequality on the lengths. So it's an if and only if sort of situation. Any questions before I move on? We'll see some examples in a second. Okay. And don't worry if it looks very abstract, like why are we doing this? We will, as we move on, I think by the end of this lecture, we will have a very strong intuition about some of this. My ink ran out here. Okay. Proof of the converse part. So converse part says that if you have a sequence of lengths satisfying this inequality, then you can create a prefix code. This I won't cover too much. Basically, it's the same construction as Shannon codes. So you sort the lengths, you pick lengths, you pick a code word according to the prefix condition, and you get a code at the end. Right. So let me not do an example. I think it's the exact same construction as the Shannon codes. Yeah, feel free to revisit. Okay. Okay, the forward part, I will do a proof sketch, which should give you enough intuition, and maybe it will help you understand the proof from last lecture better as well. So what do we need to prove? We want to prove that if you have a code, prefix code with these lengths, with lengths L1 to Lk, then this inequality holds, this one, summation I1 to k, 2 to the minus Li less than equal to 1. So this is what you need to prove for any prefix code in the world. So how will we prove it? We define something called Lmax. Lmax is the maximum. Lmax is the maximum length, maximum code word length, basically the longest code word. Okay. So this time I came prepared with a diagram. So okay, so let's see what what we can. So I've drawn here the actual code, all the code words on a tree. And I've shown the depths of the different leaves. So L1, L2, L3 are at the same depth. L4 is the deepest node in the tree, which is same as L max, because that's the deepest one, right? Now, this is something I think we saw last lecture, that 2 power L max minus Li is the number of descendants of the ith code word at depth L max. Right, so we saw this last time. I won't dwell on it too much. Basically, the idea is if you have a binary tree of depth n, then the number of leaves is 2 to the n. Right, so if you are at depth Li already, and then you need to go to depth L max, so the binary tree starting at Li up to L max has number of leaves 2 to the power, like the difference in the heights. So let me illustrate it here. Like if you see at this part, right? So this is L1, this is the node L1. And this is the sort of subtree that you can like create, which is the children of this guy. And this has number of nodes, which is like 2 to the L max minus L1, number of leaves. And so on for this guy, so on for this guy, and so on. Okay. The other property we will use is that if we have node I and node j, their descendants cannot overlap. Why can't they overlap? Because prefix free property, right? So you can see it, and sometimes it's easier to see in the picture, right? Like clearly these guys can't overlap because they are just like separate branches of the tree. So therefore, if you add all of these up, you add all of these guys who are at depth L max, their sum will be lower than the total size of the number of nodes at depth L max. So this, like we are using a very like simple property where like if you have a bunch of disjoint subsets and you add up their sizes, that cannot be more than the total size of the entire set, right? So summation of this thing is less than equal to L2 to the L max. Yeah, let me give you a minute to absorb this, and if you have any questions, please ask.
Li, L2, all of these, they're like the number of branches before you get to the leaf.
Yeah. So it's sort of, yeah, that's one. Like it's the depth or it's the length of the code word. That's the way to think. Yeah. So like L1 is like 1 because this is 1, right? L2 in this example is 3 because there are like 3 things. Yeah. I think this is the last time you will see this tree style proof. So if you don't like it, this is the end. Okay, let me move on. Okay, we'll go to the quiz. Before that, let me just say that last lecture, if you remember, we talked about prefix codes, but we also talked about a bigger category of codes called uniquely decodable codes, which were like basically lossless codes. And here, as you see, we are proving Kraft's inequality for prefix codes. In the homework, you will prove Kraft's inequality for uniquely decodable codes, which is just a more powerful statements because prefix codes are a subset of uniquely decodable codes. So, and that's a very different proof style. So I hope you enjoy that one as well. Okay, let's do the quiz questions, and here we will do some examples of Kraft's inequality as well. So this will help you get familiar with the thing. Okay, I think here I will ask for your help. So here the question was, you were given a distribution over A, B, C, D, E, and you wanted to build a Shannon code for this distribution. So you could just use that Shannon code construction algorithm. So can somebody help me with, I already like computed the lengths of the code words with this formula, right? So now you only need to tell me the code words with these lengths. Please, anybody? A. Okay, someone says 0, 0. Yeah, so the algorithm is like you just pick any available code word at that length, right? And Available means that it shouldn't be a suffix or prefix of anybody else. Okay. B. Okay, I hear 0, 1 and 1, 0. Let's choose 0, 1. Keep it simple this time. Okay, C. Okay, I see 1, 0, 1, 1. Let me again take 1, 0. So easier, more lexicographic. Okay, D. Okay, D, let's do 1, 1, 0, right? So we could, for example, we couldn't choose 1, 0, 0 because that would be like C would be, then it would violate the prefix free property. But 1, 1, 0 is totally fine. E. Yeah, so E, you see, you could have chosen 111 in a good code, but a Shannon code must have these lengths. So it's like suboptimal in that way. So we have to choose a code word with length 4. So let's choose 1110, which will satisfy all the prefix properties. Okay. And the expected length, that was question 2. I hope this is very easy now. So you just do the math, you get the 2.37. Okay. Okay, this is something that should have been on the quiz, but we couldn't add because I didn't finish on time. We just saw that Kraft inequality, right? 2 power minus Li, the sum should be less than equal to 1. So if we compute that sum for these lengths, you can do the math. You get 15 by 16, which is less than 1. So that's good. You are satisfying the Kraft's inequality. And there is a gap actually, like it's not equal to 1 here. And we'll come back to that gap in a second. Right. I hope this is very clear. So 2 power minus Li, you are summing over. So 2 power minus 2 plus 2 power minus 2 plus 2 power minus 2 plus 2 power minus 3 plus 2 power minus 4. That's the math here. And the total is 15 by 16, which is less than 1. Any prefix code will always satisfy the Kraft's inequality. Okay. Then we asked for a better code, and I already made it at home. So as some of you, I think, suggested that the last length need not be 4, right? This is clearly suboptimal. You could have chosen length 3 here. Is that clear to everyone? That you could have chosen length 3 here, right? Because 110 is also not a prefix or suffix of anything. Okay. Now if you compute the expected length, you actually get 2.25, which is strictly lower than the 2.37 we got for the Shannon code, right? So Shannon code is a good code, but it's not the optimal code. In this case, it can be better than the Shannon code. And in fact, if you now compute the Kraft sum, right, that 1 over 2 to the L and you sum it over, you actually get 1, right? So you will see maybe in the next lecture that an optimal code satisfies Kraft's inequality with equality. So for an optimal code, the summation of 2 power minus Li is actually equal to 1. So actually the gap between 1 and your Kraft sum tells you how far you are from the optimality. Okay, any questions on question 1? I think most of you got it right from what I remember. Okay, good. Second was, I think, very easy. I hope. Let's quickly solve it together. We just asked, are these codes prefix free? Was 2.1 prefix free? 2.1, some people are saying no, and I think it is not, right? Because see, D is a prefix of E, so clearly no. Okay. I hope that's clear. Okay, let's compute the Kraft sum for this guy. So it's like you have 4 terms which are like 1 by 2 square, because you have 4 things which have length 2, and then you have 1 term which has length 3, right? So this is just 2 power minus Li. I'm summing over all the code words. And if you do the math, this will be more than, it's like 1 plus 1 by 8. So it's greater than 1, right? So we saw that any prefix code has to satisfy Kraft's inequality. So if your code doesn't satisfy Kraft's inequality, it cannot be a prefix code, right? So another way to check. Okay, just by looking at the lengths, you don't even need to see the code words. Just by looking at the lengths, you know that it's not a prefix code. It cannot be a prefix code. Okay, is that clear? That like Kraft's inequality basically gives you a way to identify prefix codes. Okay. 2.2. So you have these 5. Was this a prefix code? Okay. People are nodding. Good. Yes, it was a very easy to check again. And if you compute the Kraft sum, which I think it's 5 by 8. So this is less than equal to 1. So good. It satisfies the Kraft's inequality. Great. How about 2.3? Is that a prefix code? Yeah. People are saying no. And they're correct because these two have the same. So it's a very bad code. Okay. Now if you compute the Kraft sum for this guy, it's like 3 divided by 4 plus 2 divided by 8, which is like 1. So how is this possible, right? So this satisfies Kraft's inequality. The sum is like less than equal to 1. But it's not a prefix code. Can you square that with like the results we just saw?
I could just switch.
I think you're on the right track. Like Kraft's inequality, what it says is that if your lengths satisfy the Kraft's inequality, then you can, then a prefix code exists, right? But your particular code need not be a prefix code. You could just make a code where everything is 0. So clearly it's not a prefix code. But you could make a code out of, just by slight modification of this, just make a 0, 1, and then it becomes a prefix code, right? So if Kraft's inequality is satisfied, you will get a prefix code. But your particular code may not be that prefix code, right? It could not, like, it might just be not a prefix code. Okay, are people good with that? Okay, good. Okay, let's move on. The exciting parts. So what will we do? We will talk about some information theoretic quantities. If you do an information theory course, you will see much more on these. We will just do enough for compression, basically. We will very precisely characterize what is the best prefix code. As we saw, Shannon code is clearly not the best prefix code, but it's a good one. Okay, and then we'll justify the thumb rule, which is that the length should be roughly log 1 by px, right? This log 1 by px will keep coming again and again throughout the course. And if you have done machine learning, you will see that it even comes up there where you have these log loss terms, and you have, there was a recent paper by DeepMind, the Google subsidiary, where the paper is just called Language Modeling is Compression. And we'll see that in the later homeworks and so on. Like there's a very deep connection between compression and modeling or learning in general. But yeah, just this basic thing we'll just keep talking about it. Okay, so first quantity, entropy. How many of you have heard about entropy? How many have heard about entropy in a physics context? Yeah, so see, many people are familiar about entropy from physics context, right? Where I've not done physics, so I don't know what it exactly means. So I will tell you what it means here, right? So I think it's very similar conceptually. Okay, so you have a alphabet 1 to k. From now on, we'll not talk about A, B, C, D. It's just harder to keep track of. Our alphabets will typically be just 1, 2, 3, 4, k. You have a probability distribution over that, and we'll use this shorthand notation. Pi will be the probability that x is equal to I, just to simplify our notation. Then entropy is this quantity. Sum of pi log 1 by pi. The unit of entropy is bits. We'll see why in a bit. Okay. We'll do some examples and then I will wait for questions. So one thing you notice is that entropy only depends on the probability distribution. So entropy is really not a function of x. It's not a function of the random variable. It's a function of the distribution. If you have two random variables with the same distribution, they have the same entropy. It's a function of the distribution. You can write the entropy as an expectation, right? Because you see here that like you remember that the expectation is like expectation of some y is like summation pi y xi, something like this. So is this. Okay, so here like it's just pi times log 1 over p x equal to I. That's just by the definition of expectation, right? So it's just a easier way to write it. And third thing, like if you have actual questions on this, like if you ever run into a place where you want to compute the entropy, or if you want to write it in Python, right? Like a code to compute entropy. When p is 0, this term is 0. You can either assume it or you can you use your calculus, take the limit or whatever you want to do, but this is 0, right? Otherwise you run into like not a numbers and ifs and so on in your Python script. So that's just like a definition. Okay. Any questions so far? We'll do some examples now. Okay, let's do examples. So you have a uniform distribution. So your x is uniform. X is uniform over 1 to k. Right, so what that means is like px equal to I is just 1 over k for all I. Then your entropy of x is, just use the formula from last slide, right? So p log 1 over p, that's the formula. And after you like do the math, you see log k. Bits, okay. Is that clear? Good. Have you seen log k in any other context for uniform distributions in the past? In the last like 2 lectures basically. Let me just remind you, you might remember that log k is actually the length of the fixed length code for, or I guess the ceiling of log k, right? So you already see that there is some connection between entropy and the length of a code, and we will explore that shortly. Right, so in particular, if x is like Bernoulli half, right? So Bernoulli random variables, this just means that uniform over 0 and 1. Then h of x is log 2, which is 1 bit. So if you have a random variable which is either 0 or 1 with equiprobability, then it has 1 bit of entropy. Right. Okay. Let's just compute it for this one also, just so we are very comfortable with the calculations. So half log 1 over, you will have some questions in the homework, in the quiz and the homework. Times 2, so this is like half log 1 plus 1/4 log 2 plus 1/8 times 3 plus 1/8 times 3. So half plus 6/8. Seven by 4 according to helpful audience members. Okay, so as a sort of exercise which I would encourage you to do at home, if you have this code, if you create this code for this distribution, then if you calculate the expected length of the code words, yeah, just compute it at home and you will find that it's the entropy. So again, you see some connection between the average length of the code words and the entropy. Okay, any questions about, for now you should just know that given a distribution, you follow this exact formula and you know the entropy. That's it. And we'll see more shortly. Properties of entropy. So for a random variable that takes up to k values, the entropy is between 0 and log k. We already saw when it's log k. It's log k when it's a uniformly distributed And it is 0 when it is deterministic. By deterministic, we mean that X takes exactly one value with probability 1. So it's like, it's not random, it's deterministic. So again, for a random variable that takes values in an alphabet of size k, entropy is between 0 and log k. I won't do the proofs. The 0 proof is very easy. It just depends on the fact that probabilities are less than 1. And the log k proof uses convexity and Jensen's inequality. So for those of you who are familiar with that, it's a few lines of math. Okay, so let's just talk about like what entropy means and so on, right? So entropy is like, it's like a measure of uncertainty or randomness in your random variable. So if your random variable is deterministic, there is no randomness, entropy is 0, right? If your random variable is uniform over all possibilities, then it has the maximum entropy, right? So the more random your thing is, the more entropy it will have, right? So that's just like what it means. Very similar meaning in physics, I believe. Another way to think about it is the entropy is the amount of information contained in a message. So for example, let's say you have a friend who sends you messages, and like all the messages they send you are like hello. They just send the same message every time. So when you receive the message, it like gives you very little information, right? Some other person, like somebody, sometimes they say hello, sometimes they say hi. So maybe you have some information, right? So the more entropy you have, the more variability you have, more information you can capture in that message. So entropy is like the amount of information that's contained in a random variable. A deterministic random variable has 0 information. And since at the end of the day, compression is about like storing the information, entropy is also how much you can compress, and this we will see in this class, that entropy is the limit of compression. For a given random variable, the entropy is the best compression you can achieve for that random variable. And that's why the unit is bits. And if you have like ever seen these sorts of puzzles, like I have X coins and then one of the coin is lighter than the other coins and one of the coins is heavier, and I have a weighing scale and I want to like, how many minimum number of weighings should I do to get like find out the heavier coin or the lighter coin? Or you have like a bunch of contestants in a tournament and then one of the contestants is stronger, everybody else is equal. How many tournament rounds do I need? So there are a bunch of these puzzles, and many times you will see the answer is related to entropy. And you will see some of those in our homeworks. Entropy is also important for sampling from distributions. So you have a fair coin, but you want to simulate a biased coin, or you have a biased coin and you want to simulate a fair coin. All these situations, entropy comes up as the limit of things. I think we will see all of these to some extent in the homeworks, so I won't spend class time. Okay. Any questions so far? Yeah. This is mostly standard material. Let's keep going. What is this? Joint entropy of independent random variables, right? So if you have two random variables x1 and x2, which are independent of each other, then you can define their joint entropy. So one thing that's useful to think about, which in math, even programming everywhere, right? Like you have two things, but you have x1 and x2 are individual random variables, but their pair, the tuple itself, is another random variable. So the entropy of the tuple is just the entropy of the tuple. Like you don't even need to worry about like the individual random variables, right? You just think of this pair as y, right? I can just call this whole thing as y, and then this is y. So just in terms of thinking about, like if you see a more complicated object, just think of that whole big object as your y. Okay, those who are able to follow, how did I get the second step from the first step?
Because like the two random variables are independent, so then the joint probability is just a product.
Yeah. So correct answer is that since x1 and x2 are independent, the joint probability factors out as the product of the individual probabilities. Great. So we know this. And then we know the log properties. If you have forward-end properties of log, please revise them, and that they will be helpful. Right. So at the end of the day, you get that the entropy of the two variables is same as the sum of the entropies. So what we are saying is you have two random variables, they are independent. So the total information contained in them is the sum of their individual informations because they are independent. If they were not independent, then something else will happen, and we'll talk about that in a future lecture. Okay, so we already saw the first statement that if x1 and x2 are independent, then the joint entropy is the sum of the entropies. How many of you have heard the term IID? Okay, that's good. Yeah, so IID is a very common term which means independent and identically distributed, right? So you have n variables, they are all mutually independent. So not only pairwise, but like jointly, they're all mutually independent of each other. And each of them have the same distribution. So we'll often use this notation. So what this is saying is xn is an n tuple of x1 dot 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 xn. Each of them have the same distribution as x. X is sort of a placeholder random variable which is just denotes the distribution of all of these guys. So you are like maybe tossing a coin n times, right? So each of the coin toss is an independent random variable with the same distribution with some Bernoulli half or Bernoulli p. So then using the same thing sort of inductively, you will get that the entropy of the n tuple is n times the entropy of a single random variable. So entropy just adds up if you have independent random variables. If you don't have independent, then we'll talk about it in lecture 8. It's a very important use case, but for now, let's keep it simple. Any questions so far? Okay. Another quantity, don't be scared. This is called KL divergence. So this is defined on two random variable, two probability distributions. You have P and you have Q. Both are on the same alphabet. So both are on 1 to K. So P is like P1, P2, P3, Pk, and then Q is like Q1, Q2, Qk on the same distribution. So then this divergence or distance or relative entropy between P and Q is defined as this thing. I will not talk about it for now. Just you will have some examples in quiz, solve some questions, right? It's just something Pi log Pi by Qi, the sum of these things, right? Doesn't tell you much, but the properties will tell us much more. Okay. There is only one property we need, that it is positive. It's greater than equal to 0 with equality if and only if P is equal to Q. So it is in a way a distance between two probability distributions, right? If the probability distributions are similar, it's smaller. If they are not similar, it's bigger, right? So it's a way to describe the difference between two probability distributions. Proof is in lecture notes, uses convexity, then sense inequality again. Yeah. So just remember this, we will just need this property one time in our proof later. So that's why I described it. So KL divergence, Kullback-Leibler, the two people who came up with it, or relative entropy is a measure of distance between two probability distributions. It is not symmetric. So like when you think of like your functions, typically like distance functions, like Euclidean distance or L1, L2, L0 or something, most of them are symmetric. So between x and y and x, it doesn't matter. Here it does matter. You will see it in your quiz. So this is in general. It's not equal to dqp. It's fine. It's just a fact. How many of you have seen it actually? Some of you might have seen it in your machine learning classes. If you have done generative models especially, this comes up a lot. And why does it come up a lot? Because this is a distance between probability distributions, right? So all of these generative models, what are they trying to do? They're trying to, your LLMs and diffusion models and so on, they're trying to generate samples which are similar to the real distribution, right? They're trying to create human-like text. They're trying to create artistic-like images. So, but to compute the loss, like how far they are from the real thing, you need to have a loss function which determines how different two probability distributions are. And for various reasons, including the fact that it's like differentiable and everything, KL divergence is like the loss function of choice in many, many cases. So just mentioning it, you don't need it for now, but yeah. And it has some interpretation in compression, which we might talk about, or it's in the notes definitely. Okay, we'll move on from this. For now, just remember this one thing, that the KL divergence is greater than or equal to 0 with equality if and only if the two distributions are equal, right? Rest of it is just general knowledge. Okay, so we are here. So the main result of lossless compression, right? So information theory is like one of the fields where you will see results which are like very, very precise. You know exactly what's happening. For every prefix code in the world, the expected length is greater than or equal to the entropy. There is no prefix code for any distribution, right? There is no prefix code that can beat entropy. You cannot go better than entropy. Entropy is the fundamental lower bound. So this result is called a lower bound, or it's called a converse. And not only this, right? If I just gave this and then I didn't give you like what can you do, that would like this is a negative result in a way, right? This just tells you can't do better than entropy. But there is another result. You can achieve entropy. You can get arbitrarily close to entropy. And we will talk about maybe today or next lecture about what do you mean by arbitrarily close with prefix codes. So this is the achievability part. I will stop here for a minute. I'll let you digest this and then we'll move on. Okay, any questions? Good. Right, so what does this mean, right? This means that entropy is the fundamental limit of lossless compression. It's a very powerful result, and like the next several lectures, what we will be doing is trying to actually achieve entropy. All of the work, like basically lossless compression. So Shannon in his 1948 paper, he showed this result. He showed that you can't do better than entropy. And like next 50 years, even like as soon as like 2014 or something, people are still trying to find more and more efficient ways to achieve entropy. All of your lossless and lossy compressors at their very root have something called an entropy coder. Entropy coder is something that is just trying to achieve the entropy of whatever the input is. And you have Huffman codes, and you have arithmetic codes, you have ANS, you have this, and like a bunch of different ideas, all of these trying to just do this, try to achieve entropy in an efficient way. Actually, like, so after Shannon like proved this result, I think it was almost 30 years before somebody was able to come up with a method that was a linear time in computational complexity way of achieving entropy. And then more recently, people have like improved that. It's still linear time, but like better for modern hardware. Okay, same result applies to the more general class of uniquely decodable codes. So if you noticed in the last lecture, I said for every prefix code, you cannot beat entropy. But actually for any lossless code, any uniquely decodable code, you can't beat entropy. Entropy is the fundamental bound of lossless compression, whether or not you want to use prefix codes. This you will prove in, this part you will prove in the homework. And the last point is that we are, as I mentioned like a little bit before, we assume here that your things are independent, identically distributed. Don't think that like this is only useful in very specific settings. No, this is useful everywhere, and we will see it again and again. However, more specifically, we will study more general distributions in lecture 8 to 10, so a bit later. For now, we'll just stick to the IID case. Okay, any questions so far? We'll now go to the proof of this result. I think the proof is not as exciting. I think really what, if you understand this result, right, the enormity of this, I think that's the main point. The proof, we will do the proof Some of you will like it, some of you will not. Okay. Let's do the proof. Actually, proof will give you something very useful. So yeah, let's do it. Well, okay. So first we'll prove the converse. Converse is that you cannot do better than the entropy. Any prefix code in the world cannot have expected code length that is lower than the entropy. So we start with our usual regime. We assume that X is distributed according to some distribution P, and you have a prefix code with certain lengths. And what we'll try to show is that, so what are we trying to show? Let's write it down so that it's very explicit. We are trying to show that summation I equal to 1 to k pi li is greater than equal to the entropy of P. Okay. Okay, so now some of the proof will be very like, why are we doing this? But we will do it anyway. So now let's define Qi as another distribution where Qi is defined as C times 2 power minus Li, where C is defined as this quantity. So here you see I wrote that C is equal to 1 over summation 2 power minus Li is greater than equal to 1. Can somebody explain why this holds?
Isn't that just like from like the Kraft's inequality? This one over that?
Yes. So the answer is that this is Kraft's inequality, right? So we said that we will prove this for prefix codes, but somewhere we need to use the fact that it's a prefix code, right? Like it's clearly not true for general. Like if you didn't want a lossless code, you could just have a code where every length is 0 or every length is 1. So yeah, like lossless codes can't be better than entropy. Your like non-lossless codes can be better than entropy, right? So this is where we will use the fact that it is a prefix code. A prefix code, we saw that it's like an if and only if condition, right? Prefix codes, if and only if Kraft's inequality. So we use this here. Good. Okay. And then we do a quick check, right? The C is like a normalization factor, right? Like oftentimes like you have something and then you want to convert it into a probability distribution. So you divide it by the sum so that it becomes a probability distribution. So that's what we did here. So summation of Q is just like this thing where you can, after you substitute the value of C, you will very easily check that the sum is actually 1 because the terms will cancel out. Okay. So with all this, what we did was we already had a probability distribution P, and now we created a new probability distribution Q, where Q has all these lengths inside it. So now we have two distributions, and we just read about a way of using two distributions. We will use the KL divergence, right? And we already saw the property that KL divergence is greater than equal to 0. So let's just use it. And again, right, like I didn't prove this quantity, but I'm not cheating. You can like read it. It's like a 4-line proof. You just need to know Jensen's inequality from convexity. So yeah, I hope you can trust me with this. Okay. So now math, just moving around terms. Yeah, I won't do it. I think just read it at home, like to understand like some of the moving of variables from here to there. Let me focus on the main parts. So here you write it down. Write down the KL divergence. It's greater than equal to 0. Good. Then next step, let's write it here. So you basically split the log. Very simple operation, right? You move out the Qi term here in the second term. Okay. Now this term, this left term is actually the negative of the entropy. If you remember the definition of entropy, it was pi log 1 by pi. So here you have not the denominator, so it's the negative of the entropy. Sorry. Okay. So from here to here, you move hx to right hand side, right? And I would encourage you to like go over it in peace at home. Then we had this term with a qi, right? We substitute qi here, so you get this c times 2 to the minus li. Then you have expectation. You can basically open up this log again, split the log, and let's not do this. Let's just focus on the result. Like after you do all of this, what you will get is you will get that expectation of the length is equal to this, which is greater than this term because of Kraft's inequality, which is greater than equal to entropy. So long story short, like this is what you get. This is the main result, that expected length is greater than equal to entropy, right? Don't worry about the like specific stuff. Like really, this is what we care about. It. We get the result. It's just mathematical manipulations plus Kraft's inequality plus scale divergence positive. Like these are the three things we used. Now, oftentimes, like when you prove an inequality, you want to see when does equality hold. So let's do that. If you follow all the calculations carefully, you will see that there are two conditions you need. One is that C must be equal to 1. So now, let's go back to what C was. So this was C. So what does C being equal to 1 mean? It means that Kraft's inequality must be satisfied with equality, right? We saw before that, like we saw two codes before. One was a suboptimal code, and we saw Kraft's inequality was not satisfied with equality. And then we saw an optimal code where Kraft's inequality was satisfied with equality. So basically for an optimal code that achieves entropy, C has to be 1. So you have to satisfy Kraft's inequality. So let's write it down. So Kraft's with equality. Okay. And the second thing you get out of the thing is that Pi must be equal to Qi, which basically gives you the thumb rule. So you can achieve entropy if you can satisfy Kraft's inequality and you follow the thumb rule. You follow that length is log 1 over Pi. So that's the fact basically, yeah. So you cannot do better than entropy, and you can do equal to entropy if you satisfy Kraft's inequality and your lengths are log 1 over P. So you satisfy that thumb rule we saw before. Okay, let me stop here. And read it at home, it's easy. Don't read it, it's fine. Yeah, just remember the results.
I'm just curious. I like those two things, like Kraft's inequality being satisfied in the equality, and then the probabilities being.
Yeah.
Like, are those two things like almost the same? Because like I imagine if the probabilities aren't exactly log 2, then Kraft's inequality wouldn't be satisfied. Like, could you satisfy Kraft's equality and still not have them be like perfect log 2 probabilities? Like, are those two the same or are they different?
That's a very good question. So one thing to notice is that Kraft's inequality is purely a property about the lengths. There is no probability in there, right? Kraft's inequality is just a property about the lengths of the prefix code, right? So it is independent of any distribution, right? So if you have a code that doesn't satisfy Kraft's inequality with equality, it cannot be the optimal code for any distribution. It's just a bad code, period. Like it's that's sort of one thing to think about. However, the thing you said is that for a given distribution, if you do not have Li equal to log 1 over Pi, if you have Li's which are bigger than that, then yes, you will not satisfy Kraft's inequality. So, no, I take it back. No, you can still satisfy Kraft's inequality because, okay, maybe it's worthwhile doing a quick example here. Okay, so the question was like the two conditions for equality, are they the same, one and the same, or are they different, right? So basically, so Kraft's has no P basically, right? It's just a property about L, right? So now if I make a code which is like this, yeah, okay. So we already checked before, right, that this satisfies Kraft's with equality, right? So this here, like summation 2 power minus Li, you can easily verify that this is 1. Okay, now if you take A, B, C, D and you take the probability distribution, which is like this is 1 by 8, this is 1 by 8, this is 1 by 4, this is 1 by 2. You see, you can probably see that this is not the right code because D has the smallest probability, highest probability, but you are giving it a very long code word, right? So here you see that Li is not, Li is not equal to log 1 over pi, but it does satisfy the Kraft's inequality. So you do need both properties.
Yeah, that makes a lot of sense.
Yeah. But basically, Kraft's is just about the lengths and whether it's an optimal code in that sense, right? However, I think there is the opposite side, which I should mention that. And then we'll move on. Is that if Li is indeed equal to log 1 over pi, then you can do it very easily, some calculation, which is like you do 2 power minus Li, right? And then you put it in log 1 over pi, and you do the 2 power log thing, you get pi, and this is equal to 1. So this implies that Kraft's with equality, right? So one of them implies the other, not the, it's sort of situation.
I think that's kind of what I was like thinking about, like one would mean the other one, but it doesn't go the backwards.
Yeah. Okay. Any other questions? Right. Okay. Now the other part. We said that not only is entropy like you can't do better than entropy, but you can do as good as entropy. So this is the topic of discussion for next several lectures. Today we will see like the start of the discussion. We already saw Shannon codes, right, which achieve this length, right? And we saw that if you achieve these lengths, log 1 by px, you are going to be very close to entropy. Just in the last few slides we saw. So now let's like make it very formal. So if you have lengths equal to log 1 over px ceiling, then the expected length is this summation pi times li, which is summation pi times ceiling function of log 1 over px. Okay. Say this is, it's 1 over pi. Yep. Now this is just like a general thing about ceiling functions, which you may or may not have seen, which is that ceiling function of x is bigger than or equal to x and it's less than x plus 1. So it's like somewhere between these two things. So you can put the second part, we just need the second part, that the ceiling is less than x plus 1. So you get that the expected length is less than pi times log 1 over pi plus 1. So you get this plus a second term. What is the second term? What is this term? Summation 1 over pi. Sorry, just summation pi. Yeah, 1, right? Because the probability is sum to 1. So what we have shown is that for Shannon codes, the expected length is less than hx plus 1. And we already know for any prefix code, expected length cannot be more than 1, more than hx. So therefore, we have found codes which are in this very narrow window between hx and hx plus 1, right? So we have already gotten super close to the entropy. We are like 1 bit away from entropy. Is that okay? Okay. And there is something called a dyadic distribution where all the probabilities are powers of 2. We have been seeing some of those in our examples. So when you have things that are all powers of 2, then your logs become perfect integers. Your ceiling functions are equal to your x's. And for those very special cases, you have the expected length actually equal to the entropy. So you can like exactly achieve entropy for these dyadic distributions. And actually you can't achieve entropy exactly for any other distribution. So dyadic distributions are really the only distributions. So dyadic just means all probabilities are powers of 2, like 1 by 2, 1 by 4, that sort of thing. But you can get very, very close, as we'll see in the next or 2 days later. Okay. So Shannon code is within 1 bit of entropy. That's what we showed. Now some of you who might have been like observing very closely might remember that I promised that we will get arbitrarily close to the entropy, right? This doesn't seem like that. We are like 1 bit away from entropy. If your entropy is like 0.00001, then I am like 1.00001. I am like thousands of times more than entropy. I'm very, very far away from entropy. So even though this looks like a very like powerful thing, it is not. There is still like a long way to go, right? So yeah, it is not quite arbitrarily close, right? This is just not true. Okay, so now I will ask you for help on an exercise. So you have a uniform distribution over 1, 2, 3. Just 3 things, uniform distribution. What is the entropy of this uniform distribution? Why is it log 3? Okay, because it's a uniform distribution, right? Yeah, we saw before that for a uniform distribution over k symbols, it's log k. So for 3 symbols, it's log 3. Can somebody compute log 3 for me? Log 3 base 2. Did you calculate or do you remember? Okay, nice. So I hear 1.58 bits, roughly. I think that's correct. Okay, nice. For let's make a Shannon code. We have time. Let's make a small. So for Shannon code, like the symbols will have length this log 3 ceiling, so which is 2. So a Shannon code might look like this, where you have A, B, C, A is 0, 0, B is 0, 1, C is 1, 0. What is the expected code length of this Shannon code? So the expected length is 2 because all of the code words have length 2, right? Here the Shannon code is just the fixed length code we saw like a long time ago in the first lecture. Okay, so you already see this big overhead, right? 1.58, 2, and the bound is 2.58. It is like hx plus 1. So clearly the Shannon code is between entropy and entropy plus 1, but it's worse than entropy. It's like roughly 25% worse than entropy. There is a gap. There is a gap from entropy to Shannon codes. Do you think this code is optimal for this distribution? Let me make a new slide. Let me ask you. So yeah, let's do this properly so that we are on the same page. So we have this. So we have x, we have p of x, we have log 1 over p of x. So 2, 2, 2. And then we made this code word cx, which is like 0, 0, 0, 1, 1, 0. We can make a better code word, right? Better code. And I guess for the code word we saw, for this the expected code length was 2. Let's make a better code. So if we draw, let me just make it. So it's 0, 0, 0, 1. We don't need to have this 0 after 1. I can just make it a 1. This is still prefix free. And we computed entropy was 1.58 before. Okay. So what is the entropy, what is the expected code length of this guy, 00011? Few people say 1.67. Let me just check. So it's 2 by 3 plus 2 by 3 plus 1 by 3. So it's 1.67. Nice. See, we got close. We got closer. Right? We were at 2 bits. Now we are at 1.67. So this code that you see on the far right, it's a Huffman code for this distribution. And that's our next lecture. It is the optimum code for this distribution. You cannot do better than this. But it's not still at entropy, you might observe, right? It's still 1.67 versus 1.58. There is a gap. Anybody has ideas how we can remove this gap?
Is it like for every epsilon that you, for like every degree of closeness, there exists a length of the alphabet? So you would have to have like a much longer alphabet.
But this is the alphabet you are given. How can you create a bigger alphabet starting from this? I see a few reasons. Yes. So both of you are on the right track, basically. Block coding, right? You need a bigger alphabet in this case, right? This alphabet, you can't do better, right? There is only so much like with one symbol you can do. But you saw in homework 1, if you remember, you had a uniform fixed length code over 9 symbols, and then you made it over 81 symbols, and you got better, and then you can keep increasing it. And the result will be something like that like for every epsilon, there exists a block size n such that you can get within epsilon gap of the entropy. So that's what we mean by arbitrarily close. Right. So clearly we are not at achievability. We are like not there. So this thing we will solve with Huffman code. We saw that Shannon codes are sometimes just bad, like they and you will see an example in the quiz today where they're like absurdly bad. So Huffman code is the solution here, and you will see that in the next lecture. Somebody says block codes, right? And block codes are good, right? So they can achieve entropy. You can show that they achieve entropy. We will probably do that early in the next lecture. But there are issues with block codes. It just gets exponential. Bigger and bigger blocks, you have to keep around these huge tables. It's exponential complexity, it's not great. So we'll first look at block codes. Then we will look at something called arithmetic codes, which get the same result, but much more efficiently. And then we will look at something called ANS, which again gets the same result, but even more efficiently. So there is a sequence of codes, all of them used in a bunch of real life data compressors. They're themselves data compressors. So this will be like sort of the plan for the next two weeks, basically, to look at all these different codes and understand there are various very cool ideas, like Huffman codes are based on trees, arithmetic codes are based on arithmetic, ANS codes are based on some number systems, and so on. We have 4 minutes. Let me do something on block codes, unless we have questions. Okay. This will be very short and simple, and then we'll do some examples in the next lecture. This is just so that you go home satisfied that we have proved that you can achieve entropy. Okay. So if you code in blocks of n symbols, what will happen? So if you remember that the entropy of xn was, if you have like IID symbols, right, you have independent identically distributed symbols. So the entropy of xn was n times hx. I hope everybody remembers. Okay. Now, the Shannon code on n symbols will obviously be bigger than entropy. You cannot beat entropy. And it's less than the entropy hxn plus 1. Yep. Let me write down the this thing. I expanded the entropy term. Let me divide by n, right? Because what we care about is per symbol how much I'm paying, not per block. So per symbol is like divided by n because I have a block of n symbols. Done. That's it basically. Yeah. If you work in blocks of n, you can get within 1 by n of entropy. Yeah. Before we go, let's quickly look at this example. I think this might be interesting, right? Here we didn't do in blocks at all. Okay, so this is not a good. Next lecture we'll do an example. But everybody able to follow this? So we basically code in blocks of n symbols. So what you do is you take n symbols like you did in the first quiz, and you code over that joint alphabet, right? So if you had ABC before, now you have AA, AB, AC, ... right? You have 9 symbols. You make a Shannon code, you make a big tree with 9 symbols. Then you code those 2 at a time, sort of, right? 2 at a time. And Shannon code, the property holds for any distribution, right? It will hold for the joint distribution also. It will hold for the n tuple also. The same property, this property that we proved before, that you are between hx and hx plus 1. That holds for arbitrary things. And then you divide by n and you get basically this result that you can get within 1 by n of. So within 1 by n of entropy. So this is what we call like arbitrarily close, right? So this is the proof of the achievability part. Yep. Okay. Happy to answer any questions. It's my office hour, I believe, today.